Welcome to today's session. In today's session, we will be discussing about the shear force and bending moment diagrams for simply supported beams subjected to uniformly varying loads and combination of loads. So first let us see the case of uniformly varying load, and before that the sign convention that we follow for shear force and bending moment is as shown in the figure. So if the force is to the left upwards, it is taken positive, and to the right downwards it is taken positive, and vice versa. That means force to the left downwards and to the right upwards are taken with negative sign. Similarly for bending moment, the sign convention is upward force which causes sagging bending moment is taken positive, and the moment caused by downward forces causing hogging moment is taken negative. This was discussed in previous sessions also. First, let us see the case of simple case of beam subjected to uniformly varying load, that is a triangular load. It is a triangular load. The intensity of loading here varies from W at one end to 0 at the other end. So the first step here is to calculate the reactions at supports. So how will you calculate the reactions? For calculating reactions at supports, we apply the condition, equilibrium condition, sigma MA equal to 0. So from this, taking moments about A of all the forces including reactions, we get RB into the distance is L, moment of the reaction RB about A. Okay, and this is anti-clockwise actually, and sum of anti-clockwise moments is equal to sum of the clockwise moments. That is the meaning of this equation. So RB into L on one side and the moment of the loading on the other side. The moment of loading is the distributed load, total load will be obtained by calculating the area. The area of the triangle gives the total load. So half into W into L. This is the area of the triangle. So that is the total load, and multiplied by the distance of centroid from, this is the resultant load of this varying load actually. So which is WL by 2, half into W into L. So it acts at a distance of say 1/3 of L, because this is the base for this triangle and centroid lies at a distance of 1/3 of L by 3 from base. So we are taking moments about A, which is the base of the triangle here. So the distance of centroid will be L by 3. So force total load multiplied by the distance L by 3. So this gives the reaction at B, RB, which is WL by 6. WL by 6. And RA is obtained as total downward load minus RB. Total downward load is WL by 2 minus RB WL by 6. So this gives WL by 3. So the reaction at A is WL by 3 and reaction at B is WL by 6. Okay? Yeah, that's what is shown here in the figure. So first we will find out the reactions. Next we consider a section at a distance x from B here. We are taking it at B for convenience sake. Okay, it can be taken from A also, but taking the origin at B for this case will be convenient. Okay, so the section is considered at a distance x from B, and at this section the intensity here is varying from 0 at B to W at A, isn't it? So the intensity at a distance x is obtained by using the property of similar triangles. Okay, yeah, this is one triangle and this one is another triangle which are similar. Okay, so from which the property of similar triangles is the ratio of corresponding sides is equal. Okay, so if the intensity here is W dash at x, intensity at x is W dash by W, they are corresponding sides, by x by L. X is this distance, this side of the triangle, and L is this side of this triangle. These two are corresponding sides. Okay, so W dash from this is equal to Wx by L. Okay, Wx by L. The intensity of loading at any section is given by Wx by L. Okay, yeah. Now let us consider the shear force at section x. Shear force at section x. Yeah. The shear force at section x is considering right hand side. What are the forces acting to the right of the section? We have to the right of the section we have only the reaction RB and the load, triangular load. Okay, this is section x. So reaction RB is WL by 6, that is calculated now. Okay, and this load, this triangular load. Okay, that triangular load, distributed load means total load is given as area of the diagram, isn't it? So shear force at x is equal to let us see this case. Shear force at x is now consider this. Shear force at x is given by RB. RB is upwards and on the right side, so it is negative. Right side upwards forces are negative. Okay, so shear force at x is minus RB and downward force is this varying load. Okay, so the intensity here is Wx by L. So what is the total load? Half into base into height. Height is Wx by L. Okay, so this is minus WL by 6 plus Wx square by 4. Wx square by 2L here. Wx square by 2L. Okay, yeah, this is Wx by L here. So now if you observe this, shear force at x varies parabolically. So shear force along the length of the beam varies parabolically because it is dependent on x power 2. Okay. So it is in the shape of y, it is in the form of y equal to a plus bx square. So which is the equation for parabola. Okay. So now putting x equal to 0, you will get the shear force at B at x equal to 0. This becomes WL by 6 minus. Okay. So that is what is the shear force at B. And now at x equal to L, you will get shear force at A. And what is the shear force? WL by 6 plus WL square by 2L. That is minus WL by 6 plus WL by 2. So which comes out to be WL by 3, which is nothing but RA actually. So okay, shear force at A is RA. It is positive. This is positive. So if you see here, the shear force is changing from positive to negative, isn't it? WL by 3 plus WL by 3 at A to minus WL by 6 at B. Okay? It means at some point in between, the shear force becomes 0. That means it changes sign. Okay? From positive to negative. And the location of that point where the shear force changes sign is obtained by equating this shear force to 0. So by equating this shear force to 0, you will get Wx square by 2L equal to WL by 6. Okay. So from this, you will get x square equal to W cancels. X square equal to 2L square by 6 or L square by 3. Okay. From this x is L by root 3. So at a distance of x equal to L by root 3, the shear force changes sign. And at that point, the bending moment will be maximum. At the point where the shear force changes sign, the bending moment is maximum. Okay. And that bending moment is obtained, maximum bending moment, by substituting x equal to L by root 3. Now let us consider the bending moment at x. Bending moment at x. So what is the bending moment at x? Considering previous figure. So what are the forces acting on the right hand side? RB into x minus, in this case RB into x is positive because it is producing sagging bending moment, and moment due to load is hogging moment, that is negative. Okay. So what is the total load on the right hand side? Wx by L into x by 2, this is the area, into distance of centroid from the section x, which is x by 3, 1/3 of x base, okay, side. So this is WL by 6x minus Wx cube by 6L. Wx cube by 6L. So this is the bending moment equation. Okay. Now by substituting different values for x, you will get bending moment at different points. Putting x equal to 0, you will get bending moment at B, and which is 0, which is 0. Okay. Similarly, by that is at x equal to 0. At x equal to L, you will get bending moment at A. The section will be at A when x equal to L. And what is that bending moment? You replace x by L here. So WL by 6 into L minus WL cube by 6L. So this becomes 0 again, because WL square by 6 minus WL square by 6. This is 0. Okay. So we can conclude here, for a simply supported beam, the bending moment will be 0 at the supports. The bending moment will be 0 at supports, because the supports will not restrain the rotation. The supports are not restraining rotation here. So the bending moment is 0. Okay. Yeah. And bending moment at some point C, where x is equal to L by root 3, at x equal to L by root 3, where the shear force changing sign. Okay. This bending moment will be the maximum bending moment. Okay. So you replace x by L by root 3 minus W x cube here. So WL cube by 6L into cube of root 3. That is 3 root 3 actually. Okay. So you'll get this value as WL square by 6 root 3 minus WL square by 18 root 3. So this comes out WL square by 6 root 3 into 1 minus 1 by 3 into 1 minus 1 by 3. Okay, that you will get 2 by 3 here. So W L square by 9 root 3 you will get. Okay, the bending moment at C, which is maximum, because the shear force is changing sign at that distance. Okay, it is clear. So that will be WL square by 9 root 3. Okay, now you can see the shear force and bending moment diagrams, which are shown in the previous slide here. Yeah, you can see the shear force diagram. Okay, so here this distance is L by root 3, what we are talking about. Okay, and the shear force at A is, as I told you, this sign convention here for shear force is exactly opposite to that what we have assumed. Okay, so actually this is positive for us. Okay, positive shear force for our sign convention. So WL by 3 you will get positive. Okay, understand? And WL by 6 here negative. Okay, is this clear? Yeah. And at a distance of L by 3 you will have L by root 3 you will have 0 shear force. Okay, yeah, like this you will have our shear force diagram for our sign convention. Okay, what you have followed, left side upwards and right side downwards positive. Okay, with this sign convention we will get the diagram like this, shear force diagram. And bending moment diagram you can see here, at x equal to L by 3 the distance is measured from end B, because the origin for x is taken from B. Okay, so the distance x is measured from B, L by root 3. At L by root 3 from B, the bending moment is maximum, and that is equal to WL square by 9 root 3. You can see this. Okay, WL square by 9 root 3. Is this clear? Yeah. That's how we will find out the shear force and bending moment diagrams for simply supported beam with uniformly varying load. Uniformly varying load. Now let us see another example. So here the simply supported beam is subjected to point loads, 3 point loads. So here we consider 4 different sections here. we consider the beam AC, CD, DE and EB. 4 portions we have. Okay. So for every change of loading, we consider one section, isn't it? And before that, we will find out the reactions. By applying the condition sigma MA equal to 0, you will get RB or VB here. VB into total span is 8 meters. Total span is 8 meters. So VB into 8 is equal to 4 into 1.5. We are taking moments at A. Okay. So distances from A we will take. Plus 10 into 4 plus 7 into 6. Okay. So this gives VB, which is equal to 6 plus 40 plus 42. So it is about 88. You will get 88 by 8, that is 11 kilonewtons. That is the reaction at B. So knowing reaction at B, we get reaction at A by subtracting VB from the total downward load, which is 21. Total downward load is 4 plus 10 plus 7, that is 21 minus VB, that is 11. Okay. That is equal to 10 kilonewtons. VA is 10 kilonewtons. Okay. Yeah, once you find this reactions, we draw the shear force and bending moment diagrams for this. Okay. Yeah, in simply supported beam, first we find the reactions. Okay. And this is 7 kilonewtons, 10 kilonewtons and 4 kilonewtons. 1.5, 2.5, 2 meters. A, B, C, D, E. It is clear? Now, consider different sections here. First, consider section in portion AC. Portion AC. And take origin from left, A. Okay? So, if you observe this, in this portion, X varies from 0 to 1.5. Why do we need to consider so many sections? We need to consider one section between CD, one section between DE, and one section between EB. Okay? You can take origin on either side, left or right, it doesn't matter. Okay? Yeah, for these two sections, we will take origin from left, and for these two sections, we will take origin from right. As per our convenience, we will take the origin. Okay? So, for first section in portion AC, the limits for X will be 0 to 1.5. Because the equation for shear force or bending moment, what we write here, will be valid between these two limits. And in the portion AC only it is valid. If the section crosses C, then the loads that come into picture will change. Okay. Yeah, if it crosses C, then the 4 kilonewtons load also comes into picture. Okay. Understand? So, shear force at X, considering the portion AC, is equal to VA, which is 10. Positive this is. Left side upwards is positive. And shear force at A and shear force at C is equal to 10 because it is independent of X, you can observe. And also we have concluded that when there is no load between 2 points, then shear force remains constant between those 2 points. Okay. And bending moment varies linearly between those 2 points, between which there is no load. Okay. So shear force at A and C will be equal, 10 kilonewtons. And coming to bending moment, what is the bending moment at X? It is VA into X, that is 10 into X. and it is positive because it is sagging moment. It is positive. Okay. So what are the limits now? The limits for x. Yeah, we substitute x equal to 0. We get bending moment at A, which is 0. As I told you, at supports for a simply supported beam, the bending moment will be 0. And at x equal to 1.5, you will get bending moment at C, which is 10 into 1.5, that is 15 kilonewton meters. Okay. Similarly, we consider the portion CD, portion CD, and the section in portion CD is taken with origin at A only. So the limits for this x, because this is valid between portion CD only, between point C and D. Okay, this section is valid in CD, portion CD. So the limits for x are from 1.5 to 4, 1.5 to 4. Okay. Yeah, when x is equal to 1.5, the section lies at C, and when x equal to 4, the section lies at D. So origin here is taken from A. Understand? So what is the shear force at x? Shear force at x is 10 minus 4, that is 6 kilonewtons. And this remains constant between C and D. Shear force at C and shear force at D are equal to 6 kilonewtons. Okay, it is constant. Now bending moment at x is 10 into x minus 4 into x minus 1.5, distance from x. Okay. Yeah, now by substituting x equal to 1.5, you will get bending moment at C, and this term becomes 0. You will have 15 kilonewton. If you observe here, bending moment at C, considering CD portion and considering AC portion, will be the same. But shear force at C is not same. Shear force at C, considering portion AC is 10 and considering portion CD is 6. Because here in portion AC, we consider this section at C just to the left of load. Okay, understand? So the 4 kilonewtons load does not come into picture. Whereas for shear force at D, considering CD portion, we consider this section at C just to the right of load. Just to the right means the force 4 kilonewtons comes into picture. Okay, so that's why we have subtracted 4 here from 10. So here at C, exactly at C, the shear force changes from 10 to 6. And there is a drop in the value of shear force by 4 kilonewtons, which is nothing but the load acting at C. So wherever a point load is acting, there will be a drop in the value of shear force or rise in the value of shear force by an amount equal to the load acting at that point. So now bending moment at C is 15, and at x equal to 4, bending moment at D is 10 into 4, 40 minus 4 into 2.5, 10, that is 30 kilonewton meters. So that means the shear force varies linearly from 15 to 30, 15 to 30 between C and D. Okay. In a similar way, we consider the sections at E and B ante in portion EB and also in portion D. Okay? Yeah. Considering portion BE, we can see the shear force at B and shear force at E is equal and equal to minus RB. Minus because it is upwards on the right side. So what is RB? 11. Okay. So shear force between B and E remains same, minus 11. And coming to bending moment at E is positive here because this load reaction causes positive bending moment, sagging bending moment. Okay. So 11 into 2, 22. So bending moment at E is 22. And bending moment at B is 0 because at simple support the bending moment is 0. Understand? Similarly, considering portion DE, bending moment at E is 22 and bending moment at D, if you consider, you could already have calculated 30, you will get the same value here also. Okay. So 11 into 4, 44 minus 7 into 2, 14. So 44 minus 14 is 30 kilonewton meters. And how about shear force? Shear force remains same at E. Shear force remains same at E and D. And what is that shear force? Minus 11 plus 7. That means minus 4. Minus 4. Okay. So there is a rise in the value of shear force from minus 11 to minus 4 by an amount equal to the magnitude of the load acting at E. Okay. Yeah. Now with these values we can plot the bending moment and shear force diagrams. For that you consider this figure. In this figure the shear force diagram can directly be drawn because it involves only additions and subtractions. Okay. Without these calculations we can directly draw the shear force and shear force diagram. So starting from A, the shear force is 10 and between A and C it is same. Okay. And here there is a drop in the value of shear force to 6 and which remains same up to D. And at D, there will be a drop in the value of shear force by 10. So 6 minus 10 is minus 4. Okay. Yeah. And between D and E, it remains same. And at E, there is a drop again in the value to 11. 4 minus 7. Minus 4 minus 7. That is minus 11. Okay. Yeah. This is 11. This is negative and this is positive. Is this clear? Yeah. Now, bending moment diagram. Coming to bending moment diagram. Yeah, we generally draw the bending moment diagram and shear force diagram in line with loading diagram. That will be clear and easy to understand actually. Okay. So let us draw here. Okay. Bending moment at B is at A is 0 and at B it is 0 and at C it is 15, at D 30. Okay. Yeah, 15 here and 30. And at E, bending moment is 22. And this is all positive bending moment. This is all positive bending moment. Okay. Yeah, A, B, C, D. Okay. So this is the bending moment diagram and shear force diagram for the given simply supported beam with point loads. Now, let us take one more example on simply supported beam. It has a uniformly distributed load acting over portion AC only. It is not acting over the entire span. Okay, a partial UDL of intensity 18 kilonewton per meter is acting over AC for a length of 4 meters from A. Total span of the beam is 9 meters. So here we find the reactions again. So for finding reactions, we apply condition sigma MA equal to 0 or sigma MB equal to 0 to eliminate one of the unknown reaction actually. Okay. So VB into 16, VB into 9, VB into 9 is equal to, this is anti-clockwise, and clockwise movement is due to loading 18 into 4. This is the total load, and distance of centroid, the resultant acts at 2 meters from A, at middle. So VB is 16 kilonewtons. VB is 16 kilonewtons, and therefore VA is 18 into 4 minus 16. Total downward load is 18 into 4. So 72 minus 16. And this gives how much? 72 minus 16. 56 kilonewtons. 56 kilonewtons. Okay. Yeah. Once you find reactions, next step is to calculate the shear force and bending moment at different sections. So we consider here two different sections between AC and BC. Okay, because there is a change of loading, we consider two different sections. Okay, and here let us consider first portion AC. Let us calculate here portion AC. The limits for X, we have considered section X here in portion AC with origin at A. Okay, considering left hand side, the shear force, the limits for X here are from 0 to 4. Now shear force at section X is VA minus W into X. Okay, W means here the intensity of loading. What is VA? 56, and intensity of loading 18 X. So if you observe, the shear force depends on X. Here X defines the position of section between A and C. Okay. So substituting X0, you will get shear force at A as 56. And substituting X equal to 4, you will get shear force at C as 56 minus 18 into 4. How much? Minus 16 kilonewtons. So if you observe here, the shear force is changing sign between A and C. At A it is plus 56, at C it is minus 16. So somewhere in between it is 0. Okay, and where is that point? Is obtained by equating the shear force to 0. So by equating this shear force to 0, you will get 18x equal to 56, or x equal to 56 by 18. So this you will get 56 by 18, whatever it may be, it is. So it is 28 by 9. So 9 3 is 3.11 or something. You will get 3.11 meters. Okay. So you consider now bending moment. Bending moment at x. Bending moment at x, which is VA into x, that is 56 into x minus W x into x by 2. The W x square by 2. Here W means intensity of loading, as I told you. It is 9x square. So 56x minus 9x. So substituting x equal to 0, you will get bending moment 0 at the support at A. And substituting x equal to 4, you will get bending moment at C. Now, what is the value bending moment? 56 into 4 minus 9 into 4 square. So it will be 224 minus 144. 224 minus 144, that is 80 kilonewton meters. Okay, 80 kilonewton meters. Understand? Now, by substituting x equal to 3.11, we will get bending moment at some point, say E, which is maximum. Okay, you will get maximum bending moment where shear force is changing sign. Okay, so substituting x equal to 3.11, you will get maximum bending moment. Understand? Yeah. Similarly, you consider the section between BC at x equal to what are the limits for x here? 0 to 5, because we have taken origin from B. Origin from B. Okay. So consider shear force at x, which is minus 16 kilonewtons. So shear force remains constant between B and C. It is independent of x. So at B and C, it is equal. It remains same, minus 16. And what is the bending moment at x? 16x. It is 16x. And x is 0. When x is 0, bending moment at B will be 0. And when x equal to 5, bending moment at C will be 16 into 5. That is 80 kilonewton meter. Okay. Yeah, for these values, we can draw the bending moment and shear force diagrams. Okay. Yeah, the shear force diagram here will be something like this: minus 16 and minus 16, and it varies to plus 56 here, plus 56. Okay, yeah, minus 16 to plus 56, and this distance at point, say A, C, B, at point E, the shear force is changing sign, and this distance is calculated as 3.11. Okay. So now this is positive shear force and this is negative shear force. Okay. As per our convention. Next, bending moment. Coming to bending moment. At B it is 0, at A it is 0, and at C it is 80. At C it is 80. And in between BC, it remains straight line. It varies linearly. Okay. And between A and C, it varies parabolically. It varies parabolically. Okay. Understand? It varies parabolically here. And to draw parabolic curve, we need at least 3 points. Okay, and we know the bending moment at E, which is maximum at x equal to 3.1. So you locate this point and you join these points like this. Okay, this is maximum bending moment at 3.1, where the shear force changing sign. Okay, so these are the bending moment diagram and shear force diagram for the given simply supported beam. Okay, with this we can end our session here. Okay.
Like, share and subscribe. Hit the bell icon for more updates.